Hello friends, welcome back to the channel. Hope you are doing great. If you haven't subscribed to my channel yet, please go ahead and subscribe. I have created bunch of playlists to cover various categories of the problem such as trees, graphs, dynamic programming, stacks, queues, linked list, breadth first search, depth first search, binary search, and so on. Please check them out. I have put all the playlists in the description section below. Also, I have uploaded the code for this particular problem to the GitHub repository. You can get the link from the description below this video. Let's jump into today's problem. Course schedule 4. There are a total of n courses you have to take labeled from 0 to n-1. Some courses may have direct prerequisites. For example, take course 0. You have to take course 1, which is expressed as a pair 1, 0. So basically there are 0 to n-1 courses. So n courses basically. And there are prerequisites for some courses. That's what it says, right? Some courses may have prerequisites. So the prerequisites are given as in the form of like a two-dimensional array 1, 0. That means in order to take course 0, right, you have to take the course 1 first. That's what it is. So you need to take course 0, but before taking 0, you need to take course 1, right? So after taking 1, then only you can take course 0. That's what it means. Given the total number of courses n, a list of direct prerequisite pairs and a list of query pairs, you should answer for each query whether the course query of I0 is a prerequisite of course I1 or not. Return a list of boolean, the answers to the given queries. So please note that if a course A is a prerequisite of B and if course B is a prerequisite of C, then course A is a prerequisite of C. So basically there is a transitivity relation that we are talking about here, right? So it says A is a prerequisite of B. So that means you have to go through A to go through B, right? And then B is a prerequisite of C, right? So that means A becomes a prerequisite of C. So it's not a direct, so you probably will be given with AC and BC, that's it. So from here you need to actually deduce saying AC, right? So in the input, this is only given. Input is only this one, right? Only up till this, but we have to deduce this. AC, right? Sorry, AB, this one. AB is given and BC is given. But you need to deduce AC is also a valid prerequisite, saying in order to take C, you need to take A also. That is also a prerequisite. That's what it says, right? Please note that if a course A is prerequisite of B and course B is a prerequisite of C, then course A is a prerequisite of C, right? So essentially C has two prerequisites, that is A and B, right? But between A and B, you should do A first and then B, right? So that's what it is, right? So there are transitive prerequisites. So we just looked at only these three, right? So this can be going further, right? This can be going further. So you need to deduce. Some of them will be given here, but not all of them, right? So you need to deduce some of those relationships, right? The prerequisite relationships, right? So what we are going to do for this particular problem is we are going to have some slight imagination. So imagine all the courses are nodes in a graph, okay? So all the courses, so 0 to n-1. So that means your graph has n nodes labeled 0 to n-1. And prerequisite, each prerequisite we are going to imagine it as a edge, okay? So that means there is an edge from 1 to 0, or in this particular case there is an edge from A to B, B to C, C to D, D to E, something like that. So there are 4 edges in here in this case, right? So likewise there are prerequisites, we are going to imagine them as edge in the graph, and each course is a node in the graph, right? So those are the prerequisites for our problem solving for this particular question, okay? We are saying we will have a graph where nodes are courses and edges are prerequisites, right? So let's go and try to understand through an example. So let's take a good example from whatever that is available. Okay, let's go with example 3. This actually looks better graph than others, the first or second, right? So we have essentially 3 courses named 0, 1 and 2. So 1 need to be taken first before taking 0, and 1 need to be taken before taking 2, and 2 need to be taken before taking 0, right? So that's what it is. So how many relationships are given here? 3. So 1, 2. So that means there is an edge from 1 to 2. This is the 1, and there is an edge from 1 to 0. This is 1 going up. So 2 to 0. So this is also going to 2 to 0. And these are the prerequisite courses. We are given with some queries to answer whether those are prerequisites or not, right? So let's say input is A, B and BC, right? So with that we will have only this, right? So we are given with A, B, BC. We came up with this graph, right? So let me extend just to, so that's a graph, right, for our graph. So A to B, B to C, that's a graph. And now the input was this one. So now the query given, we are given with query, right? So that's what we need to answer, right? So query, if we are given with AC, we should actually return true for this, because A is a prerequisite of C by following this, right? So we return a true. So that's what we have to return. So the what we are returning essentially here is return a list of boolean for given queries. So given there are some specific queries given, for those queries we need to answer whether that is actually true. A is a prerequisite of C. So for this case, yes, we need to return true. This is what we are going to deduce, I said, right? So those things we are asked to deduce. So in this particular case, this is a graph. So 1 is a prerequisite of 0. Yes, right? So that is straight away, since it is already given. But 1 is a prerequisite of 2. That is also true. That is also given here, right? 1 is a prerequisite of 2, 1 is a prerequisite of 0. Let's say 0, 1 is there, right? Let's say 0, 1 for this particular 0, 1, right? So is 0 prerequisite of 1, right? Is 0 a prerequisite of 1? From this graph, it doesn't look like, right? So we will return false, right? So that's what we need to come up with. So since there are n different nodes, right? And there could be any number of edges, right, between those nodes. So minimum will be at least n minus 1 edges will be there, right? Minimum. But maximum could be anything. So there will be any number of edges that could be possible. So in this case we have 3 nodes, but 3 edges are there, right? In order to have them connected, we need to have at least n minus 1 edges. But in this particular case, we have more than n minus 1 or n edges in this case, right? So now what we are trying to do is, if there is a path from given one node to another node. So since we are imagining the courses as nodes and prerequisites as edges, what are those queries we can transform? We have to see whether there is a path from A to C here in this case. So input is A to B, B to C, and queries is A to C, right? So that means what we are essentially trying to say is there a path from given node to the given node A to given node C? So we know we have a path from A to B, right? A to B, and we know we have a path from B to C. We have B to C. But do we have a path from A to C? Yes, A to B and B to C. So that is a path from A to C also, right? So this itself is a path to A to C, right? So we will say, that's the reason why we will say true, right? So let's say if a query was BA, right? So that means, is there a path from B to A? No. So we will return false, right? So if the query was BA, then is there a path? Of course there is a path from A to B, but is there a path from B to A? No. In that case we will say return false. So this is what we need to come up with. So we don't actually limit the relationships to the whatever they are given in the input, but we have to come up with whatever the possible transitive relationships also. That is one task, and then answer the queries, whether there is a path from one node to another node. In other words, for the description, right? Is there any prerequisite relationship between those two courses that are given as part of the queries? So what we are going to do is, for this particular problem, we are going to employ a algorithm called Floyd-Warshall's algorithm. Okay, so Floyd-Warshall's algorithm. So this algorithm is known for finding the paths between more than one input node to more than one output nodes, right? So we are given with several queries, right? It's not just one query. If it was a one query, then we could go with a depth first search or best first search algorithm. Then we can just, oh, okay, there is a path between two nodes or not, and then be done with it, right? But we are given with bunch of queries, not just one. So in that case, what we could do is, we could do in a different approach also. We could get a graph and then do depth first search for the queries of I0 to I1. Is there a path between those two? So we could go that way also, right? So we can do in two different ways: build a graph and do depth first search, do DFS between the query nodes, right? That's one approach. This is first approach, we will say, and this is second approach, we will say, right? So Floyd-Warshall's is one approach. Second one is building a graph and doing a DFS between the query nodes. So the reason why I did not showcase this the second approach in this particular video is, if you are doing DFS between two nodes, right, you will need to do you will probably need to traverse the same paths multiple times. So that's why that algorithm becomes much slower than the Floyd-Warshall's algorithm, right? So you need to possibly do the DFS between those nodes so many number of times. We don't know how many of them, right? So we have to cross through so many nodes. So for example, in this particular case, right, you start from A and go to B and then go to B to C, right? But what if there is something called, so from B to D is there, and from D to E is there, from E to F is there, and not just there, and from D, let's say there is something called G, right? So from G till H, right? So if there is that kind of graph is there, then you will have to traverse through all those different nodes, right? You come to A to B. Now you, for all the B nodes, so B, D, so you need to traverse D, C. Let's say the A to C, it's not A to C, but it is A to F, let's say, right? In this case, yes, there is a path, you will say true. But if there is no path, let's say, right, in that case you don't say it, right? So A to B, and you traverse A to B to C, A to B, B to D, D to E, E to F, D to G, G to H. So you'll need to traverse so much of the graph for a given two set of pairs. So in some cases you might have to traverse the entire graph for given two nodes, right? One thing could be, so let's say A and H, right? So you need to traverse the entire graph almost to come to a conclusion saying, okay, A to H there is a path, right? So for each DFS, you will have to travel through all the n nodes, right? So you have to build a graph that is going to take some time, and then you do DFS between each of those nodes in the queries, right? So it becomes a much slower approach. That's the reason why I did not showcase as part of this video. So we will look at the Floyd-Warshall's algorithm as part of this video, right? So what is the Floyd-Warshall's algorithm? So this algorithm is known for coming up with the paths between any two nodes in the graph, if there exists, of course, right? If there doesn't exist, it doesn't come with a path. But if there exists, it's going to come with a path. Okay, there is a path. And if you want, if there are weights in the path, or if there are like things like that, right? So in this particular case, there is no weight. It's just the connectivity, whether they are just connected or not, true or false. But Floyd-Warshall's algorithm has much more applications. to find out whether there is a minimum or the shortest path between any two nodes. So you will be able to use the Floyd-Warshall's algorithm to calculate the shortest path between two nodes, two given nodes in a graph. But imagine, it's not, if you are given with only just two nodes and try to calculate the path, right? Floyd-Warshall's is not the way to go. Just do a DFS, you will be done with it, because all you have to do is just only one iteration of DFS. But if you have many things, like in our queries array, we have to come up or answer many queries, not just one query. If it was one query, get done with DFS, that's it. But if there are more queries, DFS is not feasible, since you will have to traverse almost entire graphs through the DFS. That's the reason why we'll go with Floyd-Warshall's, right? So it is good application, good algorithm to come up with the paths between any two nodes, assuming you are doing that multiple times. Okay, let's get into the algorithm and the code, right? So for this Floyd-Warshall's algorithm, I am going to declare a two-dimensional array which is equal to the length of n by n, right? So in this particular case, we have declared a boolean two-dimensional array which is called reachable, which is equal to n by n, right? So I am initializing all of them, saying okay, they are not able to reach from one node to another node. That is the initialization, right? So now, by going through the prerequisites, whatever they are there in this, right, in this fashion 1 0, I am going to mark those nodes as true, right? So now I know those courses are prerequisites. Imagine, so I am talking in terms of the graph, basically saying reachability and all, but in the graph, courses are nodes and prerequisites are edges, right? So now reachability of prerequisite to the course is true. That means for this course, that is a prerequisite, I am marking it as a true, right? So that is the initialization. So still we are in the initialization approach only. So we have initialized the reachable, all of them to false, but only turn the prerequisites to true. So now we will go through the Floyd-Warshall, right? So that's the Floyd-Warshall we are going to go through. So it's a simple algorithm. So what it's going to say is, see if two nodes are already connected or not. If two nodes are already not connected, try to see if if you can connect through any neighbors, right? So the neighbors are not just the same node or the other node, but all other n minus 2 nodes are neighbors, right? So if you have n nodes, you have node 1 and node 2, you are trying to see if they are connected, right? So if they are connected, you would have already got from the prerequisites array, but now that you don't have the prerequisites, you have already filled it, that means these two are not connected, and you are trying to find if there is a connection possible. So you are going to take the help from all the different neighbors of n1 and n2 and come up with if there is a connection. So that's what is Floyd-Warshall, right? So you have the node I and j. So that means you have a node I and node j, and you made sure they are not connected. That's what I am saying. So if they are not reachable, if they are reachable already, don't worry about it. So they are reachable, you don't have to enter this for loop or whatsoever, right? So Floyd-Warshall's algorithm need not be applied since they are already connected. But if they are already connected, means already directly connected, okay? So when I am saying already connected, already directly connected. If they are not connected directly or indirectly, that's when we are going to enter this if loop, right? So what we are saying is, take a neighbor, okay, and see if that neighbor is connected to node 2. So this is node 1's neighbor, right? So node 1 neighbor, that same neighbor with node 2, right? So it's something like this. Let me represent n1, right? So there is some k node, right? So from k to n2, right? So if there is a connection like that, what we are going to say is, yes, if these two connections are true, just put all the that result, saying okay, n1, n2 can be connected. So this is a simple understanding of the flawed variables, right? So now that if you go through this particular algorithm, right, you have all the nodes which can be connected directly or indirectly from flawed variables algorithm, right? So now after this execution, you know in reachable what are reachable from I to j. Now what you need to do is you have just queries, right? Just see if they are connected, right? If they are connected, just put true. If they are not connected, put false. That's it. So now go through the length of the queue, right? And from and to. So just check in the reachable if they are true or false. Just put it them in the answer. Finally return the answer. That's it. So that's how we are going to solve this particular problem with the help of the flawed variables algorithm. Let's go ahead and look at the time and space complexity, right? Before going, right? So time, space, time. What is the time? So we know there are n nodes, right? That is given in the description itself, right? So there are n nodes. So in order to fill this particular matrix reachable, we are taking n by n, right? N into n. So order of n square. So n into n. That is the time complexity for this. And here we are going through all the prerequisites. So plus m, right? Plus m. And so coming down, we are going through these 3 for loops, right? So that will be order of n into n into n, right? So order of n and n, right? And then we are going through the number of queries which we don't know, right? So the number of queries, I'm just going to call it as order of q, right? So that will be the total time complexity for this particular algorithm. If you say, so order of n plus m plus order of n plus q. So n square plus m plus n cube plus q. So for a given n, assuming q is less than n cube, right? Then we will say the maximum time complexity is going to take is order of n cube, right? Because flawed variables is order of n cube. We are trying to find the paths between all the possible nodes, right? So if you have n nodes, you are trying to see if there is a path from any node to any node, like that. That's why the flawed variables algorithm is going to take order of n cube time. So you could simply say the time complexity for this particular algorithm will be order of n cube, but it depends on the number of queries, right? And the number of prerequisites also. So you cannot rule out m and q. So one thing that you can rule out from here is, since this is much much smaller than order of n cube, you can possibly take this away, right? You can possibly take this away and call this as a total time complexity. So I'm going to leave like right there for that time complexity. Let's go to space complexity. So are we using an extra space here? So obviously we are using the reachable, that is the extra space, and we are using m. And is there anything? Yes, we are using the answer array, right? So right, so we are using order of n into n space, right? That is for the reachable, and this is just a variable irrespective of the length, it doesn't matter. And then is there any more space we are using? Yes. So q is just a variable, we don't care much, but this is answer array we are using, right? So what is the length of the answer array? Since we don't know the number of queries it's going to have, we are going to call it as order of q, right? So the space complexity for this particular algorithm is order of n square plus q, right? So since we don't know q, if q is like very minimal, right, we just say order of n square, but since q is unknown yet, we will keep right there order of n plus q as the space complexity, right? So if you have any further questions for this particular problem, right, please post them in the comment section below this video. I will get back to you as soon as I can. I have posted the code for this particular problem to the GitHub repository. You can find the link in the description below this video. Also, all the playlists are also available in the description. You can check them out. If you haven't subscribed to my channel, please go ahead and subscribe and share among your friends as much as you can. Please click on the bell icon so that you will be notified about all my future videos. Thank you for watching. I will be back with another video very soon. Till then, stay safe. Goodbye.